So the average value of the difference between the nth partial sum of the Fourier series Sn on f and f will be the quantity 1 over p minus p, integral from minus p to p, modulus f of x minus Sn on f of x, and of course that's just 1 over 2p, times the integral from minus p to p of modulus f of x minus Sn on f of x. And so we might ask, will this quantity be small at least when n is large? It stands to reason that if we're going to get a good approximation to the function by its Fourier series, we wouldn't necessarily get that from partial sums for small n. We should take the partial sums to be sufficiently large. One thing we can do to make our lives a little easy is note that I have this 1 over 2p, this constant factor, times the integral, which ultimately depends on n. So that product, 1 over 2p times the integral, will be small, if and only if the integral itself is small. So I'll forget the factor of 1 over 2p, and instead I will put a new bit of notation in. The L1 norm of f minus Sn on f will be the integral from minus p to p of modulus f of x minus Sn on f of x. So from now on, when I write L1 norm of f minus Sn on f, I just mean this integral here. And so my goal is to get this L1 norm to be small. We have to be realistic, though. Unless f is a trig polynomial, the nth partial sum of the Fourier series for f is not going to equal f, and the L1 norm of f minus its nth partial sum is never going to be exactly 0. It's highly unlikely that we could achieve that without a lot of strong conditions on our function f. Maybe, though, it's reasonable to be more concerned about big deviations between the function f and Sn on f, and less concerned about small deviations. So what we're going to say is, yeah, there could always be some error, some discrepancy between f and Sn on f, but maybe we could measure things or penalize things so that we force the big deviations to go away. And this is sort of back-of-the-envelope fanciful reasoning. How can we make this a little more mathematical? Well, say I have a complex number, w, and the modulus of w is less than 1. Then, if I take a number r greater than 1, that forces the modulus of w raised to the power r to be less than w to be less than 1. So what does this mean? If a complex number w is small, less than 1, and I have an exponent r bigger than 1, then the modulus of w to the r will be even smaller. So by taking powers of something small, I can make that thing even smaller. And so the idea then is that large deviations between f and my nth partial sum Sn on f will stand out better if we measure an integral of the form integral from minus p to p modulus f of x minus Sn on f of x to the power r, where maybe r is something bigger than 1, not just equal to 1. And we're going to make one small change to this integral as we're measuring it. If I were to scale the integrand by alpha, so multiply f by alpha and multiply Sn on f by alpha, that would result in a power alpha to the r coming out of the integral, or modulus alpha to the r, I guess. And so you think maybe I'm stretching my function by a factor of alpha. I should stretch the measurement between f and Sn on f by alpha too. And that won't happen if I work with this integral. So instead, I'll define a new quantity via one extra power. I'll put the norm of f minus Sn on f in Lr to be the quantity integral from minus p to p modulus f of x minus Sn on f of x to the power r, whole quantity raised to the power 1 over r. So from now on, when I see the symbol norm of f minus Sn on f in Lr, I just mean this integral, where the integrand is raised to the power r, and then the whole integral is raised to the power 1 over r. And so if I can make this integral raised to the power 1 over r small for n large, I will be happy. And again, the factor 1 over r is just a nice algebraic change, so that if I scale my function by something, I scale the measurement in the integral appropriately. So here's the question. Will the LR norm of f minus Sn on f be small if n is large? And what R gives the best measurements? Is there some R that gives the best measurements? I mean, we started out taking R equals 1 in the L1 norm, and then we're starting to think maybe R bigger than 1 might highlight some properties of f minus Sn on f better. The magic number turns out to be R equals 2. And in fact, there is a powerful theorem that says the following. If you have an integrable function f from minus p to p, then the limit as n goes to infinity of the L2 norm of f minus Sn on f equals 0. So what does this say? If I measure my distance between f and my nth partial sum Sn on f in the L2 norm, if I agree that a good measurement of how small the discrepancy between f and its nth partial sum is to make this integral norm f minus Sn on f in L2 small, then I win. Then for n large, the L2 norm of f minus Sn on f is very small. And so, going back to our previous slides, if I accept the notion of good approximation being average value is small, and if I accept the definition of average value as a kind of integral, then I have shown indeed, if you believe this theorem, that the nth partial sum of the Fourier series is on average a very good approximation to f. At least when n is sufficiently large. We can get another approximation result. The nth partial sum Sn on f is not just a very good approximation when you're measuring with L2, it is the best approximation by a trigonometric polynomial. And we've seen earlier that trigonometric polynomials, not trig series, but polynomials that aren't summed over infinite numbers, just over finite, we've seen that trig polynomials are a good thing maybe to use when solving differential equations. So it stands to reason, what if we just wanted to work with an approximation of f by any trig polynomial? Which one should we use? Well, if I put g of x equal to the sum from k equals minus n to n of constant ck times e to the ik pi x over p, if that's any other sort of degree n trig polynomial, then it is also true that the L2 norm of f minus Sn on f is less than or equal to the L2 norm of f minus g. What does that mean? If I were to try to approximate f with some trig polynomial g, then the L2 norm of f minus g will always be at least as big as the L2 norm of f minus Sn on f. In other words, when you're measuring the difference between f and a trig polynomial in L2, you cannot do any better than taking the trig polynomial to be the nth partial sum of your Fourier series. So not only do we have this limit behavior, not only is the Fourier series on average a very good approximation to the function, it is the best approximation if we're looking only to approximate among trig polynomials. Here's the bad news. All of this work measuring a function relative to its nth partial sum of its Fourier series in the L2 norm says absolutely nothing on the surface about any pointwise convergence results for the Fourier series. It doesn't say whether or not the Fourier series is going to converge for a given x as a series of complex numbers, and it certainly doesn't say anything about whether or not the Fourier series will converge back to something involving the original function f. Even worse, two different functions can have the same Fourier series. Here's an example. Say I take f0 of x to be 0 for minus p less than or equal to x less than or equal to p, and say I put f1 of x to be 0 for x between minus p, possibly equal to minus p, and up to but not including p, and f1 of p will be 1. So f1 and f0 are the same function except at x equals p. What does this mean? If you drill into the integrals that give the Fourier coefficients for f0 and f1, you get f0 hat of k equals f1 hat of k equals 0 for all k. This is an integration fact. Changing the value of a function at one point doesn't change its integral. Moreover, both of those Fourier coefficients, f hat of 0 and f hat of 1, are 0 for all k. They're not just equal, they're both 0. So the Fourier series for f0 and f1 do converge, but to 0 for all x. So certainly the Fourier series for f1 doesn't converge back to f1. So what's the problem? Fourier coefficients of two different functions are equal. Fourier series of two different functions are equal. The two functions themselves are not equal. So you might ask, what is the point anyway? If all we can get is some good approximation of f in L2, and if we, to get better convergence results for the Fourier series, demand some sort of continuity or differentiability property on f, what's the point of even trying with Fourier series? Here's one answer. We conclusively have, if you believe the theorem on the previous slide, that Fourier series are very good approximations to their functions, at least from the point of view of the L2 norm. Nothing in life is exact. Few things in science outside math are exact. Not all things in math are exact. It is okay to be content with just an approximation to a function, to a set of data, and the Fourier series can give you that in a very good way. Second, we're going to see, not this week but next week, but Fourier series can help us find formal solutions to differential equations, both of the ordinary and partial ilk. That is, we can use some techniques from Fourier series that we have yet to develop to show that Fourier series can help us construct candidates for solutions to differential equations. If you have a differential equation and you don't know what the solution is, you'll take anything that even might look possibly like a solution, and then you'll hope you can prove it's a solution. So with these formal solutions that we'll construct from Fourier series, we will then do some magic, some work, and we'll prove those candidates really are solutions. This is often the way we work backwards in math. We get something that looks like it might be a solution, and then we do some other rigorous work to prove it is a solution. So for these two reasons, the very good approximation properties of Fourier series in a world in which few things are exact, and the to-be-determined properties of how Fourier series interact with ordinary and partial differential equations, I claim that Fourier series are very worthwhile and valuable, even if their exact pointwise convergence is messy or impossible.